Hello students, continuing our lectures on integral transforms. So this will be our third lecture. So we have previously discussed about integral transforms in my lecture number 142 and 161, where I have discussed about the basics of integral transforms and something about the Fourier transform in details. So in continuation to that, I will start with some applications of Fourier transform. Now, we consider the wave equation. That means del square u by del x square is equal to 1 by c square del square u by del t square. With the initial conditions that u x 0 is equal to fx and del u by del t at x not equal to 0 is equal to 0. Now what we will do here, we will first write ux as in terms of Fourier transform. So we can write let uxt is equal to 1 by root 2 pi minus infinity to plus infinity the kernel gkt e to the power ikx dk. So this is how we mention ukx. Now the second step is to we will just replace with the given differential so that we can write one by root pi. That means we shall be using this equation. Del square u by del x square is equal to 1 by c square del square u by del t square. So we will substitute this in this format. So what we will obtain is the following expression: 1 by root 2 pi minus k square into minus infinity to plus infinity gkt e to the power ikx dx is equal to 1 by c square. Now this part 1 by c square 1 by root 2 pi into minus infinity to infinity del square g by del t square e to the power ikx dk, so it will be dk. So ultimately on simplification the expression that we will obtain is del square g is function of k and t by del t square is equal to minus c square k square gkt. So on solution of this differential equation is gkt is equal to a into the power ICKT plus b e to the power minus ICKT. Now we started with the initial condition that x0 is equal to fx. So in that case fx will be equal to 1 by root 2 pi minus infinity to infinity gk0 e to the power ikx dk. Therefore gk0 is equal to the inverse Fourier transform minus infinity to infinity fx e to the power minus ikx dx. Now the next boundary condition was del u by del t at x is equal to 0 is equal to 0. So we can write del u by del t is equal to 1 by root 2 pi minus infinity to infinity infinity. Is equal to 1 by root 2 pi minus infinity to infinity del g by del t e to the power ikx dx is equal to 0. Or we can write del g by del t function of k and 0 now is equal to 0. So we get expressions of the constants in the solution as equal to half gk 0. So the solution of the differential equation that we initially started is the following. So we can write gkt as equal to half gk0 into e to the power ict plus e to the power minus ict. So using this value of gkt in the initial expression that we started, we can write uxt is equal to 1 by root 2 pi minus infinity to infinity and we'll put the expression of g here, that is half g k 0 e to the power ict plus e to the power minus ict, this will be g into dk to the power ikx dk. So we can write this one as equal to 1 by root 2 pi minus infinity to plus infinity into half gk0 multiplied by e to the power ik x plus ct plus e to the power ik x minus ct dk. So what we have done here, we have simply taken this ikx inside the bracket. So this is the solution. So we can write this one as again equal to half of the function of f x plus ct plus f x minus ct. So this is how this is one of the applications of the Fourier transform. Now the Fourier transform can also be solved for an unknown quantity. For example, if there is an unknown quantity phi x in a solution, in the equation, like phi x is equal to, say, fx plus lambda minus infinity to plus infinity k from x is equal to fx plus lambda minus infinity to plus infinity k x minus ct phi t dt, where these two are considered to be the known function fx and kx minus t. They are considered to be known functions of x and t. Now, such an equation where the unknown motion occurs inside the integral is known as the integral equation. Unknown equation is inside the integral. So we write it in a different form. Say we write is as an integral equation. We mentioned that Ix, the basic integral equation, is equal to root 2 pi, basic form, minus plus infinity, then x c minus x minus ct phi t dt, thus phi x is equal to fx plus lambda into root 2 pi ix. So here this getting, sorry, so this got multiplied to this ix, and the expression that is left is simply fx simply ix, so it will be lambda into root 2 pi into ix, and fx remains as it is. Now in this condition, if we take the Fourier transform of both sides, so taking Fourier transform of both sides, so let me write the equation once again. So we have obtained that phi x is equal to fx plus lambda root 2 pi ix. Now we are taking Fourier transform on both sides. This is what we are doing. So after that we are obtaining the following expression. We are obtaining the Fourier transform of phi x is equal to the Fourier transform of fx plus lambda into 2d into again the Fourier transform of ix. So there are three Fourier transforms involved in the equation. This one, first one, second one, and third one. Now we have derived the convolution theorem. So according to convolution theorem, Fourier transform of function fx and function ix is equal to dash kx into f of fx. So we'll use this Fourier transform into the present condition. So our present condition is this. So using the convolution theorem, the expression that we're obtaining is Fourier transform on phi x US this will remain the same. Fx, only thing that will change is f of ix, so that will be lambda by 2 pi, so this is a constant. So lambda into 2 pi remains as it is, and the change occurs only in fx, so it will be Fourier transform of kx into Fourier transform of phi x. So from this we can write that the Fourier transform of phi x is equal to Fourier transform of fx divided by 1 minus lambda 2 pi Fourier transform of kx. Now in this case, if we have gk, fk, and kk, if these represent the Fourier transform, if declare the Fourier transform of phi x, fx, and corresponding kx, then simply we can replace fx, kx, and phi x by their corresponding Fourier transforms. So we get gk as equal to fx, fk into 1 minus lambda root 2 pi kk. So we initially started, our main objective was to find the known function fx. So fx is now, as we have started using it in terms of Fourier transform, was 1 by root 2 pi minus infinity to plus infinity gk e to the power I k x dk. So we'll simply replace this gk by this expression. So the next step will be is equal to 1 by root 2 pi minus infinity to plus infinity. So writing gk, we will simply write fk. There is a different color here. Fk 1 minus lambda root 2 pi kk into the remaining expressions e to the power I k x dk. So this is the final expression. So these are some of the applications of the Fourier transform. Now next we will take up Laplace's transform. So we had initially discussed about Laplace's transform in our previous lectures. So let's recall it. The Laplace's transform is given as if there is a function ft and we do a Laplace's transform, and it's called the function of fs L of ft, and it is simply equal to limit a tends to infinity 0 to a e to the power minus st. This becomes the kernel ft dt. This is the expression of Laplace's transform. Now we will take up some of the Laplace's transforms, like suppose there is a equation C1 f1x and C2 f2x. So if we take the Laplace transform of these two functions, it will be equal to 0 to infinity C1 f1x plus C2 f2x into the expression e to the power minus px. So instead of s, we are using here p instead of into dx. So f and so here there is a replacement. From this expression to the expression, replacement is s is being replaced by p and x is being t. T is being replaced by x in the additional plus equation. So continuing to simplify, so this becomes, if we separate the two equations, it becomes C1 0 to infinity e to the power minus px f1x dx plus C2 0 to infinity e to the power minus px fx f2x dx. So that is again equal to C1 L f1x plus C2 L f2x So we have obtained the property of linear combination of functions, that Laplace transform of C1 f1x plus C2 f2x is equal to C1 f1 Laplace transform written separately for two equations. Now, as we have an inverse Fourier transform, similarly we have an inverse Laplace transform too. So, if Laplace transform has been done for function fx to obtain a function fp, then if we do the inverse Laplace transform on fp, we will get fx. And this linear combination, Laplace transform for linear combination of functions, this property also holds for this inverse Fourier transform. So that means if Laplace transform of f1x is equal to f1p, and Laplace transform of f2x is equal to f2p. Then again the linear transform, Laplace transform of c1 f1x plus c2 f2x is equal to c1 f1p plus c2 f2p and also for the inverse case, so this is the inverse Laplace transform. So this for the inverse case we can also write c1 f1x plus c2 f2x is equal to inverse Laplace transform of c1 f1p plus c2 f2p. And it is assumed that f1 is f1x is equal to inverse Laplace transform of f1p, and f2x is again equal to the inverse Laplace transform of f2p. Now let us take some problems. Suppose fp is equal to 2 by p to the power 4 plus 3 by p square plus 4. Now we need to have certain relationships we need to have in advance to proceed this. So first of all is Laplace transform of 1 is equal to 0 to infinity. It will be to the power minus px dx, and it is equal to again minus 1 by p e to the power minus px 0 to infinity. So it was again equal to 1 by p, where p is greater than 0. So Laplace transform of 1 is 1 by p with p greater than 0. Similarly, if we have a Laplace transform of x, so it will again equal to 0 to infinity x e to the power minus px dx. So it will be equal to minus d by dp of 0 to infinity e to the power minus px, taking integration by parts, and it will be simply equal to 1 by p square for p greater than 0. So this was the first expression, and Lx is equal to 1 by p square for p greater than 0. This is the second expression. Similarly, we have been given x to the power n. We need to find out the last power of this power of n. So we again start with 0 to infinity, x to the power n e to the power minus px dx. So let's write it once more. Laplace transform x to the power n is equal to zero to infinity x to the power n e to the power minus px dx. It is again equal to minus d by dp, 0 to infinity x to the power n minus 1 e to the power minus px dx. And this is equal to minus d by dp of so this is nothing but the Laplace transform of x to the power n minus 1. So this is what we get, d by dp for Laplace transform of x to the power n minus 1. So this is another expression that Laplace transform of x to the power n is equal to minus d by dp Laplace transform of x to the power n minus 1. Now, this expression, previously derived expression, we can write it in a different form. So, that's if Laplace transform of x to the power n is equal to minus d by dp Laplace transform of x to the power n minus 1. So, you can write this as equal to minus 1 by, if we keep on doing it repeatedly, it will be minus 1 to the power n. How many times we have differentiated into dn by dx dpn into L into 1. So L into 1, as we know, it is equal to 1 by p. So this expression is again equal to minus 1 to the power n dn by dpn 1 by p, and it is equal to, ultimately, it is equal to n factorial divided by p to the power n plus 1, where p is greater than 0. So again we write the expression that Laplace transform of x to the power n is equal to n factorial divided by p to the power n plus 1 where p greater than 0. Now, we have previously derived this, that Laplace transform of e to the power alpha x is equal to minus infinity 0 to infinity e to the power minus px into e to the power alpha x dx, and that is 1 by p minus a, where p is greater than a. Now we move on to the problem which we started. We had initially started with this problem that if p is equal to a by p to the power 4 2 by p to the power 4 plus 3 divided by p square plus 4. So what we will do, this is actually the Fourier Laplace transform already given. You need to find out the expression on which the Laplace transform. That means we need to find out the fx. We need to find out fx. So sorry. And this can be obtained if we do the following operation. We do the inverse Laplace transform of fp. So the inverse Laplace transform is equal to 2 into inverse Laplace transform of p to the power minus 4 plus 3 into inverse Laplace transform of 1 by p square plus 4. So from previously we have derived that this expression p to the power n, so this will be equal to 3 factorial divided by not 3 factorial, 1 by 3 factorial into x cube and this will be equal to 1 by 2 sine 2x. So the expression ultimately fp is equal to 2 into 1 by 3 factorial x cube plus 3 into 1 by 2 sine 2x. So this is our what we are looking for, and this is equal to fx, which we intended to find. Now there are some relations which we should know about Laplace transform, and Laplace transform of sine ax sin alpha x is equal to alpha by p square plus a square. So this is how this expression was derived, and similar to that we have Laplace transform of cos alpha x. It will be equal to p by p square plus a square, and Laplace transform of sine hyperbolic alpha x is equal to alpha by p square minus a square. So this sign only changes if we are replacing ax by the hyperbolic function. Okay, so our next problem that we will take up is to find out the inverse Laplace transform of the expression fp as equal to 2p plus 1 divided by p square minus 5p plus 6. So first we need to write it in a different form. So we will write this one as equal to C1 is a coefficient of p minus 2 plus C2 p minus 3. So we've written this because p square minus 5p plus 6 is equal to p minus 2 into p minus 3. So therefore fp is now from here we can write it is equal to C1 plus C2 p minus 3C1 plus 2C2 divided by p minus 2 into p minus 3. You just taken it from this. So this again now we so this is actually equal to 2p plus 1 initial expression divided by p square p minus 2 and p minus 3. So this numerator, this part, it should be must be equal to 2p plus 1. So we can write the numerator as c1 plus c2 into p minus 3c1 plus 2c2. This should be equal to 2p plus 1. So if this is the case, then from here, from comparing these two, we can see that c1 plus c2 is equal to 2, and this expression 3c1 plus 2c2 is equal to 1. So we ultimately, solving this, we come out that c1 is equal to minus 5 and c2 is equal to 7. So our job now simplifies. So now we have to only find the inverse Fourier transform of the following expression. It will be inverse Fourier transform of minus 5 p minus 2 plus 7 p minus 3. And using the expression of using this expression that e to the power ax is equal to 1 by p minus a, this we find a solution as equal to minus 5 e to the power 2x plus 7 e to the power 3x. So this is our final solution that we looked for. Now, apart from this, another property which may be useful in finding the inverse Laplace transform is called the shifting property. Now it says that Laplace transform of e to the power alpha x fx is equal to f p minus alpha. That means it gets reflected in the Fourier transform, in the Laplace transform. So let's try to understand this. So let's take from the left hand side LHS. If we expand it, it will be 0 to infinity e to the power minus px into e to the power alpha x fx dx. So it will become equal to 0 to infinity e to the power, it will be minus p minus alpha x fx dx, and it is simply equal to f p minus alpha. Now this shifting property can be used to find the inverse transform as well. So let us use this to see how it can be used. So the expression of the function of p is 3p plus 1 divided by p square plus 2p plus 5. So it can be simplified as 3p plus 1 divided by p plus 1 whole square plus 4. So it can again be written as equal to 3 into p plus 1 divided by p plus 1 whole square plus 4 minus 2 into p plus 1 whole square plus 4. The reason that we did this change, that means from 3p plus 1 to expression, because we wanted to have something in the form of fp minus alpha, because we will be using the shifting theory. So this expression actually satisfies this p minus alpha expression. So now in this case, the inverse Fourier transform of fp is now simply equal to the inverse Fourier transform of so inverse Laplace transform of 3p plus 1 divided by p plus 1 whole square plus 4 plus the other expression. So let us write it down in a fresh manner. Inverse Laplace transform of fp is now equal to 3 into inverse Laplace transform of 3p plus 1 in brackets divided by p plus 1 whole square plus 4 minus inverse Laplace transform of 2 divided by p plus 1 whole square plus 4. So we use the shifting theory here. According to shifting theory, we write it once again. Laplace transform of e to the power ax fx is equal to fp minus a. This is the shifting theory. So using this shifting theory, the first expression, this expression, it turns out to be equal to, so 3 liminalities into e to the power minus x into cos 2x. So because we have used also a cos, because L of cos alpha x we know is equal to alpha by p square minus alpha square, p square plus alpha square. So this is the first expression, and the second expression here is minus e over x into sine 2x. So here this minus x is due to this plus 1, and e to the power x is due to again this plus 1. So for the cos 2x it gets as minus x, for sin 2x it gets as plus x. So this is the ultimate solution, that L inverse Fp is equal to 3 to the power minus x cos 2x minus e to the power x sin 2x. Okay. So the next topic is how to find out the Laplace transform of derivatives. Laplace transform of derivatives. That means that we need to find out this Laplace transform of del f by df by dx, for example. So according to the rule, this should be equal to 0 to infinity e to the power minus into df by dx into dx, and so proceeding further by duration of parts, so this becomes e to the power minus px into integration. If we do the integration of this one, so it will be fx. So here it is fx, sorry, fx, and limit is from 0 to infinity, plus here it's minus, so differentiation of it to the power. This is the first function. So now we differentiate this, so minus p, then minus of minus p becomes plus p. Then we can add integrating 0 to minus px and fx dx. So this is nothing but equal to minus function of 0 plus p, and this is nothing but again the Laplace transform of fx. So it is equal to p into Lfx. So now here, so let us write it once again. So what we obtained is Laplace transform of df by dx is equal to f of o of 0 minus f of 0 plus p of Laplace transform of fx. This is the equation that we have obtained. Now we have assumed that limit x tends to infinity e to the power minus px fx, it tends to 0. So the first one actually is based upon this. Now this is the necessary condition with Laplace transform fx to exist. Now f0, this expression, it actually implies that limit p tends to 0, f0 plus a small increment is equal to f0 plus a small increment. So this is the expression. Now what if this df by dx, what if there is a derivatives of higher order? For example, d squared f by dx squared. Has to find out this. So we can write it as equal to L of d by dx of f dash x. We write it in this fashion. That means d squared f by dx squared is equal to d of dx of f dash x. This is the expression that we are using. We intend to use the relationship that we recently derived, that is L of Laplace transform of df by dx is equal to minus f0 plus Laplace transform of fx plus p into Laplace transform of fx. We actually intend to use this expression, so that is why this is a transformation of writing d square f by dx square as d by dx of dash x. So Laplace transform, if we proceed, then Laplace transform of d square f by dx square is written as equal to, if we are using this expression, it is again equal to minus f dash 0 plus p into L Laplace transform of f dash x. So this is, again, we need to expand it, this expression. So we will do it as in this case. So this is again equal to minus f dash 0 plus we take p common into minus f0 plus L of fx. So that is again equal to minus f dash 0 plus minus p of f0 plus L of so there will be p squared. Sorry, you want p here, so it will be p squared. Write it once again. L of p squared f dx squared is equal to minus dash 0 plus p minus p of 0 plus p squared L of x. So the next topic is to find or to understand the convolution theorem in terms of involving Laplace transform. So we have the convolution theorem for Fourier transform. Now we'll write the convolution theorem. Different colors here. Laplace transform. First, we start with two Laplace transforms. Suppose there is a Laplace transform of f1x gives f1p and Laplace transform of f2x gives f2p. So if this is the case, then the convolution theorem it actually states that inverse Laplace transform of f1p into f2p is equal to zero to x f1 x minus t into f2t so we write it once again. Minus 1 f2p f1p to f2p is equal to 0 to x f1 x minus t into f2t dt. Now, if you look into the integral, say, if you look into the integral, any integral Ix, for that matter, if it is equal to 0 to x f1 x minus t into f2t, so it can also be written as the opposite case, if it written as 0 to x. Instead of writing f1 x minus t, you can write it as f1t into f2 x minus t dt. So this is actually the convolution of the function f1 and f2 in the interval 0 t. So here's convolution of the functions f1 and f2 in the interval 0x. Now let us try to derive this. So f1p into f2p, it is equal to 0 to infinity e to the power minus px f1x dx multiplied by 0 to infinity e to the power minus px f2x dx. Now let's use a different parameter here. Instead of writing here f2, let's use t f2t dt. So this now is equal to 0 to infinity and again 0 to infinity e to the power minus p x plus t f1x dx. This is for integration over dx, so this one closes into f2t integration over dt. Now we will assume that let x dash is equal to x plus t to replace this one. So we can, the expression now changes that f1p into f2p is equal to 0 to infinity, again 0 to infinity e to the power minus p x dash, since we're using this, into f1. So if x dash is equal to x plus t, so x becomes now x dash minus t. So f1 x dash minus t into dx dash, then f2t dt. So we have in a fresh format. So f1p f2p is equal to 0 to infinity, 0 to infinity, e to the power minus px dash into f1 x dash minus t px dash into f2 t dt. So in this integral above, for the given value of t, for the given value of t, first the x dash integration is done. This integration is performed initially over the range t tends to 0, t tends to infinity, and next after this, so this integration will be done first, then after the integration, next that t integration will take place. So in this fashion we cover the entire area of the x dash t plane. So the area of x dash t plane is covered. Using this. And this plane lies on the right hand side of x dash is equal to t. So we have t versus x dash we plot, then, and if this is x dash is equal to t, so this plane actually lies here. Okay, so therefore, finally, what we can say is that f1p into f2p is equal to 0 to infinity e to the power minus px dash 0 to x dash f1 x dash minus t into f2 t dt dx dash, and it is also equal to L of Ix so integration f of inverse f1p plus f2p is equal to Ix. So here we can see that this is in this case the integration has been done in the opposite way. First the dt this integration has been done, and then the integration of dx dash has been done. So we can proceed it in the other way. Either you can have either you can proceed in this way, or you can proceed in this way, and whatever depends upon the order of integration that you are doing.